Hey guys, today I'm going to be making a tutorial video for the GTORangeBuilder Alpha. GTORangeBuilder is a new type of program that can solve for very precise Nash equilibrium approximations for heads-up river scenarios. So the basic idea is that you have some poker situation you want to analyze. Something happened up to the river. What exactly doesn't matter. At the start of the river, there's hand ranges for each player. There's a starting pot size, stacks, board cards. And you enter all the information to GTORangeBuilder and click Calculate, and it'll solve for game theory optimal play, or a Nash equilibrium strategy for both players. So the first step is setting up your scenario. You'll need to enter some game state information about the starting pot, the effective stacks, and whether the hero is in position or out of position. Then you'll need to enter some board cards. You can do that either by typing in a string like this, or you can click and pick your set of cards. And then you'll need to enter some bet sizes. GTORangeBuilder always assumes that you can check and that you can shove. But other than that, you'll need to enter a list of bet sizes that you want GTORangeBuilder to consider. And you can list up to 3 bet sizes. Here I'm just picking 1. The more bet sizes you pick, the kind of more complicated your scenario is going to be for you to understand, and the less precise GTORangeBuilder is going to be when solving it. Then you need to pick hand ranges for each player. This is just kind of a simple example, so I just threw in about 15% of hands for each player. And finally, you can click Calculate to see a solution. There's also a tutorial button here. If you click this, you'll get to see our tutorial. So I click Calculate, it crunches, and spits out a solution in our solution browser. So the first thing I want to highlight in the solution browser is these equilibrium EVs. This is kind of a high-level view of the strategy. We see that the hero, whose range was slightly stronger and was in position, on average wins about 23 chips of the 40-chip pot, while the villain averages 17.1. And then this Nash distance number is quite important. This is GTORangeBuilder calculates approximate Nash equilibrium, and you can actually measure using the concept of epsilon Nash equilibrium how far from a true equilibrium you are. So you always kind of want to consider this number in relation to the absolute size of the pot. So the pot has 40 chips, and this number is 0.1. So this is a very, very tight equilibrium. The way our alpha works is we kind of basically let what our solver run for about 2 seconds, and it gets as close to the solution as it can in those 2 seconds. So if you enter very complicated situations that might take 20 seconds for GTORangeBuilder to solve, it won't get very close in the first 2 seconds and will return a result that's not as precise. And you can always see how precise the result you got is by looking at this Nash distance number. And for our alpha, this is important. If you guys are finding scenarios that have a really big Nash distance relative to the pot size, please do let us know, as one of our goals during the alpha is to kind of improve the performance of the solver and get it really, really accurate in all cases. So this is our strategy browser. This kind of gives you both the high-level view of the strategy over here, and then you can drill down for details. Each of these circular nodes represents a decision point for one of the players, and these lines kind of represent a decision being made. So this is saying we started the game, 100% of the time we get here. About 84% of the time the villain checks, and we end up at this node. Of that 84%, 21% the hero raises to 20, and we end up at this node. And you can mouse over nodes and mouse over lines to learn more about them, but you can also click to really get details. So if we click to examine this node, we'll zoom in on it, and we can see for every hand in the hero's range what the optimal strategy is. So it looks like he's raising to 20 with his aces, which are kind of the top of his range, kings. You can check it out here. 7s is set, so that's the very top of his range. He's occasionally shoving. That's raising to 80, which he's doing a little more often with the top of his range. And you can also see more details here about the hero range and the villain range. This will tell you the EV for every hand and what percentage of the player's range a given hand makes up at this point in time. These percentages are not weighted by card removal effects currently, so it doesn't take into account the fact that the villain checking with certain hands changes the distribution of hero hands here. And that's kind of intentional, because the idea is that you might want to consider playing these equilibrium strategies against a non-equilibrium opponent, in which case the card removal effects will be different. At every node, you'll get to see kind of these top-level stats, what the pot is, what the stacks are, what the equal room EVs are at this point. So obviously the hero's EV went up when the villain checked because he's only checking 84%, and the other times he's betting, and he is tending to bet slightly stronger hands. So for example, he's, if we go back here to look at the villain's first play, he's checking his aces all the time, so he's kind of checking his mid-strength hands, but when he has something like a set of sevens, there he's often raising them. The only other thing I should mention about the strategy browser is that you can always take a look at things kind of node by node and start at the very end of the tree and work your way backwards. So you can kind of get a sense of exactly how the action flows by doing that. So we can see that when we get down to this node, the hero usually has aces through queens. He never has any of his air hands, really. And so working backwards is a nice way to do that. We'll see that a little more clearly in the next example I'm going to go through here. So this was kind of a big scenario with big ranges. The other kind of key use case for GTORangeBuilder is using smaller representative ranges. And the idea of a representative range is not a set of hands that you might actually likely run into in a game state, but rather a set of hands that might represent some game state in a way that's much more simple and digestible than kind of putting in the full ranges. So if you look at what I'm doing here, I give the hero queens or aces and the villain kings, and I give them exactly one combo. And you might use this as a way to represent a state where the hero's range is polarized 50-50 between the nuts or air, and the villain always has a medium strength made hand. And from a mathematical standpoint, even though queens wouldn't be considered air here, this is exactly modeling that scenario because the villain's hand beats queens always and loses to aces always. So if we could calculate on a scenario like this, we'll get a new solution here, and we kind of look at it. We can see, first off, that the nuts or air range does way better than the made hand range, which is kind of interesting because they both have 50% equity. But we can also start to analyze the solution a little more clearly now and really see what's going on. So the villain has kings, and he always checks. Then from there, we can see that the hero ships it with his aces always and his queens 2/3 of the time, and he checks back his queens 1/3 of the time. And then we keep following the tree. The villain now calls 1/3 of the time with kings and folds 1/3 of the time. And the hero was shoving his queens exactly such that the villain was indifferent between calling and folding. So often in practice, I think it's a little simpler to use representative ranges to kind of drill down on a scenario rather than using full ranges, but GTORangeBuilder can do both, and I definitely would love to hear from you guys as alpha testers what you find most useful and what features you'd like to see to make either use case more accessible. The only other thing I want to mention here are a few limitations of our alpha right now. Because we're trying to keep the computation pretty limited, if you just try and put in really giant ranges, like all hands versus all hands, it's going to tell you that the scenario is too complex and that we put some limitations in for the time being. We're going to try and relax these, but I also don't think right now that it's all that useful to find equilibrium for any two cards versus any two cards. If you are running into the complexity limitations in scenarios where you have a really useful question or you're trying to model some real-world use case, please let me know the situation so that I can try and kind of find some specific ways to accommodate the situations you guys want to look at better. I think that's it for now. If you have any questions on how to use the software or any ideas for how this tutorial could be better, please post in the YouTube comments. And thanks for watching.